In the winter of 1621, a Jesuit missionary named Pierre Biard stood on the frozen shore of what the French called Acadie, watching ribbons of green and crimson fire dance across the northern heavens with an intensity that made him forget the biting cold penetrating his woolen cassock. He had come to the New World expecting to encounter savage peoples in need of salvation, but nothing in his theological training at the Collège de Clermont had prepared him for this celestial spectacle that the Mi'kmaq hunters called the spirits of their ancestors playing games in the sky. Biard would later write in his Relations that he witnessed what he believed to be a battle between angels and demons made visible above the earth, though he carefully noted the indigenous interpretation in his margins, understanding even then that these lights had inspired human wonder long before Christian cosmology attempted to explain them. What Biard could not have known as he stood there, his breath crystallizing in the Arctic air, was that the lights he witnessed were the result of invisible particles ejected from the sun 3 days earlier, travelling across 93 million miles of void before colliding with the magnetosphere surrounding Earth, a concept that would not be articulated for another 2 centuries. The Mi'kmaq elder who stood beside him that night, a man the French called Baptiste but whose true name was Copitk, watched the same phenomenon with eyes trained by generations of accumulated knowledge passed down through oral tradition. His people had observed that these lights appeared most frequently during the coldest months, intensifying when the air itself seemed to crack with dryness, and they had developed an entire cosmology around their appearance that intertwined with hunting practices, seasonal migrations, and the fundamental structure of their understanding of reality itself. Across the Atlantic in the winter of 1716, the English astronomer Edmund Halley observed a brilliant aurora from London, an occurrence rare enough at that latitude to cause widespread panic among the populace, who interpreted the blood-red sky as a portent of divine wrath or impending war. Halley, whose mathematical mind had recently calculated the orbit of the comet that would bear his name, attempted to apply systematic observation to the phenomenon, noting in his journal the precise time of onset, the colours visible, the apparent height and movement of the luminous curtains, and the correlation with the behaviour of compass needles which spun erratically during the display. He theorised that the lights might be caused by magnetic effluvia rising from the Earth's interior, a hypothesis that would prove incorrect in its mechanics, but prescient in its recognition of magnetism's role in the phenomenon. The terror that gripped London during that display had deep historical roots that Halley himself recognised, for the chronicles of medieval Europe were filled with accounts of auroral displays interpreted as harbingers of catastrophe. The Anglo-Saxon Chronicle recorded that in the year 793, just before the Viking raid on Lindisfarne that marked the beginning of the Norse invasions of Britain, fierce dragons were seen flying in the air and the sky appeared to run with blood. Modern analysis of these accounts suggests an exceptionally powerful geomagnetic storm, possibly caused by a solar eruption of unprecedented magnitude, created auroral displays visible as far south as the Mediterranean, where Byzantine chroniclers recorded similar phenomena with equally apocalyptic interpretations. The Norse seafarers who terrorized European coasts for 3 centuries had a profoundly different relationship with these celestial lights, for in their homeland they were a regular feature of the winter sky. The Old Norse term for the aurora was variously rendered in surviving texts, with the Prose Edda referring to Bifrost, the rainbow bridge connecting Midgard to Asgard, though whether this specifically denoted the aurora or was later conflated with it by Christian scribes remains a matter of scholarly debate. Other Norse sources speak of the light reflecting from the shields and armour of the Valkyries as they rode across the sky selecting the slain to bring to Valhalla, an interpretation that suggests the Norse observed the rapid movement and wave-like patterns in auroral displays and incorporated them into their martial cosmology. When the Icelandic scholar and chieftain Snorri Sturluson compiled the Prose Edda in the early 13th century, he was attempting to preserve pre-Christian Norse mythology at a time when it was rapidly being displaced by the new faith. Yet he wrote from within the Christian worldview himself, creating a complex layering of interpretation in his descriptions of celestial phenomena. The aurora appears in his text intertwined with accounts of fire giants and the cosmic geography of Yggdrasil, the world tree. But Sturluson also betrayed an empirical curiosity that led him to describe how these lights appeared differently depending on the observer's location, noting that travellers who ventured far to the north reported the lights appearing directly overhead, while in Iceland they remained closer to the northern horizon. This observational detail, seemingly minor in Sturluson's mythological compilation, contained the seed of a crucial fact about the aurora that would not be scientifically articulated until the 20th century. The lights occur in an oval-shaped zone surrounding the magnetic poles, and one's latitude determines the angle at which they appear. The medieval Icelandic observation anticipated by 700 years the detailed mapping of the auroral oval conducted by satellites in the space age, demonstrating that systematic observation, even when embedded in mythological frameworks, could yield accurate data about natural phenomena. The Sami people of northern Scandinavia, whose territory extended well into the auroral zone, developed their own intricate body of knowledge about these lights that reflected their herding lifestyle and animistic worldview. For the Sami, the aurora carried an element of danger absent from Norse interpretations. Children were warned to remain silent and still when the lights appeared, and to never wave at them or attract their attention. This cautious approach stemmed from a belief that the lights represented the souls of the dead, but it also reflected practical observation that the aurora sometimes produced audible sounds, a phenomenon long dismissed by scientists as folklore until acoustic evidence was finally documented in the late 20th century. The question of whether the aurora makes sound had divided observers for millennia, with countless eyewitness accounts from indigenous peoples across the Arctic, describing crackling, whooshing, or swishing sounds accompanying bright displays, while the scientific establishment maintained this was impossible since the aurora occurred at altitudes where the air was far too thin to transmit sound waves. This dismissal of indigenous testimony as superstition or acoustic illusion persisted until Finnish researchers in 2012 finally recorded and measured sounds correlated with auroral activity, discovering that under specific atmospheric conditions, electrostatic charges could indeed create audible discharges at ground level during geomagnetic storms, vindicating centuries of observations that had been patronizingly discounted by Western science. In 1741, a Swedish scientist named Anders Celsius, who would later devise the temperature scale bearing his name, conducted a systematic study of the aurora with his assistant Olof Hjorta, making a discovery that would prove pivotal to understanding the phenomenon's nature. They observed that during auroral displays, magnetic compass needles deflected from true north, sometimes by several degrees, and that the magnitude of this deflection correlated with the brightness and intensity of the lights. This was the first clear evidence linking the aurora to magnetism, though the mechanism of this connection remained obscure for another century. Celsius and Hjorta were working in Uppsala, where the aurora was frequent enough to permit regular observation but not so constant as to be taken for granted, an ideal latitude for systematic study. Their meticulous records, maintained night after night through Swedish winters, represented a new approach to natural philosophy, the accumulation of quantitative data over extended periods, seeking patterns and correlations that might reveal underlying laws. This methodology would become foundational to modern science, but in the mid-18th century it represented a relatively novel approach, one that required institutional support, financial resources, and the kind of patience that immediate practical application could not justify. The question of why aristocratic patrons and royal scientific academies would fund such seemingly impractical research reveals much about the Enlightenment era's intellectual culture. The Swedish Academy of Sciences, which supported Celsius's work, had been founded in 1739 with explicit aims of advancing useful knowledge for the improvement of Swedish commerce and industry. Yet, it also supported pure research into phenomena like the aurora, precisely because the interconnectedness of natural phenomena was not yet fully mapped. A discovery about the aurora might unexpectedly illuminate the nature of magnetism, which had direct implications for navigation, which in turn affected maritime commerce and naval power, the foundations of national wealth and security in the age of mercantilism. This web of potential utility meant that even the most abstract research could attract patronage, but it also meant that scientists operated within political and economic constraints that shaped what could be investigated and how results were presented. When Celsius published his findings on the aurora's magnetic effects, he was careful to emphasize potential navigational applications, though his personal correspondence reveals he was driven more by philosophical curiosity about the structure of the cosmos than by any immediate practical concern. This tension between pure knowledge and useful application runs through the entire history of auroral research, periodically erupting into conflict when funding sources demanded tangible results from what they increasingly viewed as expensive indulgence. Across the Atlantic in the British colonies, Benjamin Franklin read accounts of Celsius's magnetic observations with intense interest, seeing in them potential confirmation of his own developing theories about electricity. Franklin's famous kite experiment of 1752, whatever its actual details might have been, and considerable doubt exists about whether it occurred as popularly described, was part of a broader investigation into atmospheric electricity that he believed might explain a range of phenomena including lightning, St. Elmo's fire, and possibly the aurora itself. In a letter to the Royal Society in 1753, Franklin speculated that the aurora might be caused by electrical particles concentrated near the poles, a hypothesis that was remarkably prescient, even though he lacked any mechanism to explain how such concentration might occur or what would cause the particles to luminescence. Franklin's electrical theories were inseparable from his political philosophy, though this connection is often overlooked in popular accounts of his scientific work. He conceived of electricity as a fluid that sought equilibrium, flowing from areas of excess to areas of deficiency, a model he explicitly compared to economic trade and political liberty, arguing that just as electrical balance produced stability while imbalance produced dramatic discharge, so too did political systems require balance between competing interests to avoid revolutionary upheaval. When he observed or contemplated the aurora, he was not merely seeing a natural phenomenon, but a potential model for understanding equilibrium and imbalance in multiple domains of human and natural existence. This interdisciplinary quality of 18th century natural philosophy meant that aurora research existed in an intellectual space quite foreign to modern specialization. The same individual might investigate the aurora, conduct economic analysis, design political systems, and invent practical devices, seeing all of these activities as aspects of a unified project to understand and improve the human condition. The fragmentation of knowledge into discrete academic disciplines was still in the future, and someone like Franklin could move fluidly between what we would now categorize as physics, political science, economics, and engineering without feeling he was changing subjects. In 1770, the British astronomer James Cook was sailing the Pacific on his first great voyage of exploration when, on a calm night near New Zealand, members of his crew observed an auroral display at a latitude where such phenomena were exceptionally rare. Cook's official artist, Sidney Parkinson, attempted to sketch the display, producing a watercolour that remains in the British Library's collections, depicting greenish curtains against the star field of the southern hemisphere. This observation was significant for several reasons beyond its rarity at that latitude. It demonstrated that auroral phenomena occurred in the southern hemisphere as well as the northern, suggesting a global rather than regional cause, and it provided data from a location where few European observers had ever been, expanding the geographical scope of auroral records. Cook's expedition carried sophisticated chronometers designed by John Harrison, instruments intended to solve the longitude problem through precise timekeeping, and the ship maintained careful astronomical observations for navigational purposes. This meant that Cook's records of the 1770 aurora included precise time, date, and position information, superior to most other 18th century observations, making his account valuable to later researchers attempting to reconstruct historical geomagnetic activity. The interdependence of navigational necessity, exploratory ambition, and scientific observation in Cook's voyages exemplified how aurora research advanced through piggyback on enterprises driven by quite different motives: imperial expansion, commercial advantage, and cartographic completion. The indigenous Maori people who observed Cook's ships arriving in their waters had their own interpretations of the rare auroral displays visible from New Zealand's latitude. In Maori cosmology, these lights were sometimes understood as the fire of Tamanuitera, the sun deity, or as reflections from torches carried by celestial beings, interpretations that located the phenomena within an intricate web of relationships between earthly and cosmic realms. When Cook's crew and the Maori attempted to communicate about what they had seen in the sky, they encountered not merely a language barrier, but a fundamental incommensurability of cosmological frameworks, each side possessing sophisticated observational traditions, but embedding those observations in radically different explanatory systems. This problem of incommensurability haunted all cross-cultural encounters over natural phenomena like the aurora. European observers, increasingly committed to mechanistic explanations grounded in matter and force, struggled to extract what they considered factual content from indigenous accounts laden with spiritual significance, often dismissing entire bodies of knowledge because they could not easily separate empirical observation from mythological interpretation. Yet the indigenous systems were frequently more sophisticated than European observers recognized, encoding in narrative and ritual form observations about patterns, correlations and variations that European science would later laboriously rediscover through quantitative methods. The Inuit peoples across the Arctic had developed a particularly nuanced understanding of auroral behaviour, distinguishing between different types of displays with separate names that reflected both visual appearance and implied meaning. The Inuit observed that certain forms of aurora appeared during specific weather conditions, that others seemed to respond to sound or movement, and that intensity varied with seasons and years according to patterns that could be anticipated, though not precisely predicted. This knowledge was embedded in survival practices, as the aurora's appearance could signal changing weather, provide light for essential winter activities, or indicate the presence of conditions that made certain types of hunting more or less favourable. When European explorers like William Parry and John Ross began their Arctic expeditions in the early 19th century, seeking the Northwest Passage and expanding British territorial claims, they relied heavily on Inuit knowledge for survival, but rarely acknowledged the sophistication of Inuit scientific understanding. Parry's expedition journals from the 1820s contain detailed auroral observations, meticulously recording colour, movement and intensity. Yet when his Inuit guides provided their own observations and predictions about the lights, these were typically recorded as quaint folklore rather than valuable data. This systematic devaluation of indigenous knowledge represented a profound missed opportunity for auroral science, as the Inuit possessed multi-generational datasets and pattern recognition superior to anything European observers could accumulate during brief expeditions. The irony of this dismissal became apparent in the 20th century when researchers analysing historical auroral records discovered that Inuit oral traditions contained references to the 11-year solar cycle, the periodic variation in solar activity that drives long-term fluctuations in auroral frequency and intensity. This cycle would not be recognised by European science until 1843, when the German astronomer Samuel Heinrich Schwabe announced his discovery of periodic variation in sunspot numbers after 17 years of daily observations. The Inuit had encoded this knowledge in stories about the auroral spirit's changing vigour, and in practical observations about the waxing and waning of display frequency across multi-year periods. But this information was inaccessible to Europeans who approached indigenous testimony with predetermined assumptions about primitive superstition versus civilized rationality. Schwabe's discovery of the sunspot cycle emerged from an investigation originally aimed at finding a hypothetical planet orbiting inside Mercury's orbit, a quest that demonstrates how scientific progress often arrives through sideways paths rather than direct assaults on a problem. While searching for this supposed planet, which he planned to detect as it transited the sun's disk, Schwabe maintained daily solar observations, counting and sketching sunspots to ensure he could distinguish them from any planetary transit. Over years of this patient work, he noticed that sunspot numbers were not constant, but varied dramatically, reaching peaks and troughs with remarkable regularity, approximately every 11 years. The connection between sunspot activity and the aurora was not immediately obvious even after Schwabe published his findings, and it required the work of multiple researchers over several decades to establish the correlation. The crucial link was forged by the English amateur astronomer Richard Carrington, who on September 1, 1859 was conducting his own systematic solar observations when he witnessed an intense white light solar flare, a brightening on the sun's surface so dramatic it was visible to the naked eye through his telescope. Carrington immediately recognised he was witnessing something extraordinary and called a witness to confirm his observation, then carefully documented the flare's position, timing, and evolution. What Carrington could not see but what was occurring as he watched that solar flare was an ejection of billions of tons of charged particles from the sun's corona, accelerated to speeds exceeding 1 million miles per hour and directed along a trajectory that would intersect Earth's orbit. Approximately 17 hours after Carrington's observation, this massive cloud of solar material struck Earth's magnetosphere with unprecedented force, compressing it dramatically and triggering the most intense geomagnetic storm in recorded history. The resulting auroral display was visible at latitudes as low as the Caribbean. with reports of the lights being seen from Cuba, Hawaii, and Colombia, regions that normally never experience auroral activity. The aurora of September 1859 was so bright that people in the northeastern United States could read newspapers by its light at midnight, and the colours ranged through the entire spectrum, with vivid reds, purples, and greens dominating different portions of the sky at different times. Telegraph systems across North America and Europe were thrown into chaos as the intense geomagnetic fluctuations induced powerful electrical currents in the long metal wires, causing operators to receive severe shocks, setting telegraph paper on fire, and in some cases allowing telegrams to be sent even after operators disconnected the batteries that normally powered the systems, the induced currents alone proving sufficient to operate the instruments. This electromagnetic chaos demonstrated that the aurora was not merely a passive visual display, but an active electromagnetic phenomenon capable of affecting technological systems, a realization that would prove increasingly significant as human civilization became more dependent on electrical technology. The Carrington Event, as it came to be called, represented the first clear evidence that events on the Sun could have immediate and dramatic effects on Earth, establishing the Sun-Earth connection that would become central to the emerging field of space weather. Yet in 1859, the scientific community lacked any theoretical framework to explain how solar activity could influence Earth. The existence of the solar wind was still unknown, the structure of the magnetosphere was unmapped, and even the concept of plasma as a fourth state of matter would not be articulated for another 70 years. Carrington himself was cautious about claiming a direct connection between his observed solar flare and the subsequent geomagnetic storm, noting the correlation but acknowledging that a single coincidence could not establish causation. This scientific caution was vindicated in the sense that what he observed, a white light flare, is not directly responsible for geomagnetic storms. Rather, the associated coronal mass ejection, which was invisible to Carrington's instruments, carries the charged particles that interact with Earth's magnetosphere. Yet Carrington's intuition that solar and terrestrial phenomena were connected was fundamentally correct, and his observation marked a turning point in auroral research from purely terrestrial theories toward recognition of the Sun's central role. In Norway during the late 19th century, the physicist Christian Birkeland became obsessed with understanding the aurora through a combination of expeditionary observation and experimental simulation. In 1890, Birkeland established an observatory at Halden in northern Norway, above the Arctic Circle, where he and his team endured brutal winter conditions to maintain continuous auroral observations, correlating the lights with simultaneous measurements of magnetic field variations and electrical currents in the ground. Birkeland's expeditions were grueling affairs, with observers sometimes trapped in their mountain station for weeks by blizzards, maintaining their instruments in temperatures that froze mercury and shattered thermometers, driven by Birkeland's relentless determination to gather comprehensive data. But Birkeland's true innovation came in his laboratory at the University of Christiania, where he constructed an apparatus he called a terrella, a magnetized sphere placed inside an evacuated chamber and bombarded with streams of electrons. When Birkeland energized this system, glowing rings appeared near the sphere's magnetic poles, creating a miniature aurora that demonstrated how charged particles interacting with a magnetic field could produce the luminous displays observed in nature. This experimental validation of the electromagnetic theory of auroral formation was a triumph of 19th century physics, combining field theory, vacuum technology, and electromagnetic manipulation to recreate in controlled conditions a phenomenon previously accessible only through passive observation of the sky. Birkeland theorized that the Sun emitted rays of electrons that traveled through space and were channeled by Earth's magnetic field toward the polar regions, where they collided with atmospheric gases and caused them to glow, an explanation that was essentially correct in its broad outline though wrong in numerous details. His contemporaries were skeptical of his claims that particles could traverse the vast distance between Sun and Earth, as the prevailing assumption held that interplanetary space was a perfect vacuum that would quickly disperse any stream of particles. This skepticism was rooted in the physics of the time, which lacked concepts like plasma and magnetic field lines, frozen into ionized gases, mechanisms that would later explain how solar particles could maintain coherent streams across interplanetary distances. The resistance Birkeland encountered to his solar particle theory revealed deep fissures in the scientific community about the nature of auroral phenomena. alternative theories proliferated, including proposals that the aurora was caused by precipitation from clouds in the extreme upper atmosphere, by sunlight scattered from ice crystals at high altitude, by spontaneous electrical discharges in rarefied air, or by various forms of radiation emanating from radioactive materials in Earth's crust. Each theory had its champions and its evidence, and each revealed the limitations of attempting to understand a phenomenon that occurred in a region of the atmosphere inaccessible to direct investigation with the technology of the period. The altitude at which the aurora occurred was itself a matter of significant debate through the 19th century, with estimates ranging from a few miles above the surface to beyond the moon. The resolution of this question required trigonometric parallax measurements, observing the same auroral display from widely separated locations and calculating its height from the differences in apparent position against the background stars. Such measurements required coordination between observers hundreds of miles apart, precise timing, and the ability to identify the same specific features in the aurora from different viewing angles, all challenging propositions given the rapidly changing nature of auroral displays and the communication technologies available before the telegraph. In 1902, a collaborative effort organised by the International Polar Year brought together observers from multiple nations to make simultaneous auroral measurements from coordinated observation points. The data collected during these campaigns finally established that most auroral displays occurred between 90 and 150 kilometers altitude in the region of the atmosphere now called the thermosphere, though some auroral forms extended as high as 400 kilometers or more. This altitude information was crucial because it situated the aurora in a region where the atmospheric density was low enough that charged particles could travel significant distances without collision, yet high enough that sufficient gas molecules existed to produce visible light when excited. The physics of how atmospheric gases produce coloured light when struck by energetic particles involves quantum mechanics at the atomic level, knowledge that would not become available until the early 20th century, when Niels Bohr developed his model of the atom with its discrete energy levels. Prior to this understanding, researchers observed that the aurora displayed characteristic colours. The green of oxygen at 557.7 nanometers was most common, with red oxygen emissions at 630 nanometers appearing at higher altitudes, and blue and purple nitrogen emissions adding variety, but they lacked a theoretical framework to explain why these specific colours appeared or what they revealed about the underlying processes. Bohr's atomic theory explained that electrons in atoms occupied specific energy levels, and when an atom was excited by collision or absorption of energy, its electrons jumped to higher levels, then returned to lower levels by emitting photons of specific wavelengths corresponding to the energy differences between levels. Each element had its own unique set of energy levels, and thus its own characteristic spectrum of emitted light, a spectral fingerprint that could be used to identify which gases were glowing in the aurora. Spectroscopic analysis of auroral light confirmed that oxygen and nitrogen, the primary constituents of Earth's atmosphere, were indeed the sources of the observed colours, with the specific hues revealing not just which gases were glowing, but which atomic transitions were occurring, providing detailed information about the energy of the incoming particles and the density of the atmosphere at different altitudes. In 1930, the Australian physicist Sidney Chapman developed a mathematical theory of geomagnetic storms that attempted to explain how solar disturbances could generate the electrical currents responsible for auroral displays and magnetic field variations. Chapman's theory involved complex calculations of how ionized gases in the upper atmosphere would respond to changing magnetic fields, creating current systems that would in turn generate their own magnetic effects. His work was groundbreaking in its mathematical sophistication, but it suffered from a fundamental flaw. It assumed all the relevant currents flowed in the ionosphere, the electrically conductive layer of Earth's atmosphere, and it did not include currents flowing along magnetic field lines between the ionosphere and space, currents that Birkeland had proposed decades earlier. This omission was not mere oversight, but reflected a genuine theoretical dispute about whether electrical currents could flow along magnetic field lines through the near vacuum of space. Chapman and his followers argued this was impossible, that currents required continuous conducting media, and that space was insufficiently conductive to support such currents. Birkeland's vision of electrical circuits connecting the Sun to Earth's polar regions through space seemed to violate established electrical theory, and in the absence of direct measurements from space, the debate remained unresolved through the 1930s and 1940s. The Second World War interrupted fundamental auroral research as scientific resources were directed toward military applications, but the war also produced technological advances that would later prove crucial for space physics. Radar development had pushed electronics to new levels of sophistication, and the V-2 rocket had demonstrated that vehicles could reach the edge of space, opening the possibility of in situ measurements from regions previously accessible only to theoretical speculation. In the war's aftermath, captured V-2 rockets were used by American and Soviet researchers to conduct upper atmosphere studies, carrying instruments above the densest layers of atmosphere to measure radiation, magnetic fields, and particle fluxes directly. These early-sounding rocket missions provided tantalizing glimpses of the space environment, but they were brief, lasting only minutes above the critical altitudes, and they could not capture the dynamic evolution of auroral events. What was needed was sustained presence in space, continuous monitoring of the conditions between Sun and Earth, and the ability to measure phenomena across large spatial scales simultaneously. The satellite age, inaugurated by the Soviet launch of Sputnik in 1957, would finally provide these capabilities, transforming Aurora research from a ground-based observational science into a multi-point space-based investigation of a vast and complex electromagnetic system. The International Geophysical Year of 1957-1958 marked an unprecedented collaboration in Aurora and geomagnetic research, with scientists from 67 nations coordinating observations during a period of expected high solar activity. Ground-based observatories from the Arctic to Antarctica maintained synchronized measurements of auroral displays, magnetic field variations, cosmic ray intensity, and ionospheric properties, creating a global dataset of extraordinary scope. Simultaneously, the first satellites began returning data from space, including Explorer 1, whose discovery of intense radiation belts surrounding Earth added a crucial piece to the puzzle of how charged particles from the Sun interact with Earth's magnetic field. The Van Allen radiation belts, as they were named for the physicist James Van Allen, whose instruments detected them, are donut-shaped regions where energetic particles are trapped by Earth's magnetic field, bouncing between the north and south magnetic poles along field lines and gradually drifting around the planet. These belts demonstrated that Earth's magnetosphere was not simply a passive magnetic field in space, but an active region where complex particle dynamics occurred, with implications for understanding how solar particles could access the upper atmosphere and generate auroras. The belts themselves glow faintly when particles collide with the sparse gas molecules in their orbits, but this is distinct from the aurora proper, which occurs when particles from the magnetosphere precipitate into the denser atmosphere below. In 1958, Eugene Parker, a young physicist at the University of Chicago, published a theoretical paper proposing that the Sun's corona was so hot it must continuously expand outward, creating a supersonic stream of ionized particles, plasma, flowing through the solar system. Parker called this hypothetical flow the solar wind, and he predicted it would carry with it frozen-in magnetic field lines from the Sun, creating an interplanetary magnetic field structure that would interact with planetary magnetospheres. The paper was highly controversial. 2 referees recommended rejection, and it was only published after the journal editor overruled them, judging that while the conclusions seemed implausible, the mathematics was sound enough to warrant presentation to the scientific community for debate. Parker's solar wind hypothesis revived Birkeland's 60-year-old proposal that particles from the Sun cause the aurora, but now embedded in a sophisticated theoretical framework that explained how plasma could traverse interplanetary space without dispersing. The key insight was that ionized plasma and magnetic fields are intimately coupled. The plasma cannot easily cross magnetic field lines, and the field lines are effectively frozen into the plasma, moving with it. This coupling meant that magnetic disturbances on the Sun would propagate outward with the solar wind, carrying regions of enhanced particle density and field strength that would strike Earth's magnetosphere like battering rams, compressing it and injecting energy that would ultimately power auroral displays. Confirmation of the solar wind's existence came in 1962 when instruments aboard the Mariner 2 spacecraft, travelling to Venus, detected continuous streams of particles flowing from the Sun with properties matching Parker's predictions. The solar wind was revealed as a highly variable flow, with speeds ranging from 300 to 800 kilometers per second. densities fluctuating by orders of magnitude, and embedded magnetic fields that rotated in complex patterns determined by their origin in the Sun's rotating corona. Within this turbulent stream were occasional massive structures, coronal mass ejections containing billions of tons of solar material that produced the most intense geomagnetic storms and the most spectacular auroral displays when they struck Earth. The 1970s and 1980s saw an explosion in space missions designed to study the magnetosphere and its interactions with the solar wind. NASA's Dynamics Explorer satellites provided simultaneous images of the entire auroral oval from space, revealing for the first time its complete structure and dynamic behavior. The oval was not a perfect circle, but an elliptical region surrounding each magnetic pole, expanding during geomagnetic storms and contracting during quiet periods, with the aurora most intense on the night side of Earth, where the magnetosphere was stretched into a long tail by the solar wind. These images revolutionized understanding of auroral morphology, showing that individual auroras visible from the ground were small segments of a vast global phenomenon, components of an electrical circuit connecting the magnetosphere to the ionosphere across thousands of kilometers. Within this circuit, the currents that Birkeland had hypothesized and that Chapman had dismissed flowed along magnetic field lines, with intensities reaching millions of amperes, making them some of the most powerful electrical currents in the solar system. These field-aligned currents, finally detected unambiguously by satellites in the 1970s, are now called Birkeland currents, in belated recognition of his pioneering vision, a reminder that scientific disputes sometimes take generations to resolve and that vindication can come long after the original proponent has passed from the scene. Birkeland himself died in 1917, never knowing that his most controversial ideas would eventually be confirmed, though his Torello experiments are now recognized as brilliant demonstrations of the electromagnetic principles governing space plasma physics. The Japanese satellite Akebono, launched in 1989, carried instruments specifically designed to study the acceleration mechanisms that give auroral particles their energy. The puzzle of particle acceleration was crucial because particles in the solar wind, while travelling fast in absolute terms, did not carry sufficient energy to penetrate deeply into the atmosphere and produce the bright emissions characteristic of strong auroras. Somewhere in the magnetosphere, particles were being accelerated to much higher energies, gaining the thousands of electron volts needed to create the vivid displays observed from the ground. Akebono's measurements revealed that this acceleration occurred in complex regions where magnetic field lines reconnected, annihilating and reconfiguring in processes that converted magnetic energy to particle kinetic energy. Magnetic reconnection, the process by which oppositely directed magnetic field lines break and reconnect in new configurations, releases enormous amounts of energy and has become recognized as one of the fundamental processes in plasma physics, occurring not just in Earth's magnetosphere but in solar flares, in the magnetospheres of other planets, in stellar coronae, and possibly in the accretion disks around black holes. In Earth's magnetotail, the stretched region on the night side where solar wind interaction stores magnetic energy, reconnection events explosively release this stored energy, accelerating particles both toward Earth, where they produce auroras, and away from Earth, back into interplanetary space. These substorm events occur regularly, typically every few hours when the solar wind is active, each one injecting fresh energy into the auroral system and triggering new displays that can erupt across the sky in minutes. The Cluster mission, a European Space Agency constellation of 4 identical satellites, launched in 2000, provided the first truly three-dimensional view of magnetospheric structures by making simultaneous measurements from multiple points in space. The mission revealed that boundaries in space plasma are not smooth surfaces, but turbulent dynamic regions filled with waves, instabilities, and transient structures that evolve on timescales from milliseconds to hours. The interaction between the solar wind and the magnetosphere occurs across the magnetopause, a boundary that ripples and undulates as the solar wind pressure varies, occasionally allowing solar wind plasma to directly penetrate into the magnetosphere through processes like magnetic reconnection, or through wave-particle interactions that were only beginning to be understood as the 21st century opened. Indigenous knowledge systems that had accumulated observations of the aurora over countless generations were finally being approached by scientists not as quaint folklore, but as valuable data sources potentially containing patterns and correlations unnoticed in the shorter observational record of modern science. researchers working with Sami communities in Scandinavia, with Inuit groups across the Arctic, and with First Nations in northern Canada began systematic efforts to document traditional knowledge about the aurora, discovering rich taxonomies of auroral forms, sophisticated understanding of temporal patterns, and observations about rare phenomena that had escaped scientific documentation. The Sami, for instance, distinguished multiple types of auroral motion and structure with specific terms, recognizing differences that corresponded to distinct physical processes in the magnetosphere, ionosphere system, knowledge encoded in language and passed through oral tradition over countless cycles of observation. One particularly intriguing element of Sami oral knowledge was the assertion that the aurora could be influenced by human action, that waving a white cloth or making certain sounds could cause the aurora to intensify or approach. Western scientists had long dismissed this as superstition, but recent research into auroral acoustics and electromagnetic wave interactions suggests there might be more to such claims than simple myth. During very intense auroral displays, the strong electric fields that extend down into the lower atmosphere can cause electrostatic discharges that produce sounds, and it is theoretically possible that movements or sounds could trigger such discharges under the right conditions, creating a feedback effect where human action appears to influence the aurora. Whether this explains the traditional Sami practices remains uncertain, but it demonstrates the risk of dismissing indigenous knowledge without careful investigation of the physical processes involved. The colours of the aurora encode information about altitude, atmospheric composition, and particle energy in ways that trained observers can read like a text. The common yellow-green colour, visible in most auroral displays, comes from oxygen atoms at altitudes around 100 to 150 kilometres being excited by electrons with energies in the 110 kilo-electron-volt range. This emission occurs promptly, within a second of the collision that excited the atom, creating the rapidly shifting patterns characteristic of active aurora. The deep red emissions that sometimes crown the tops of auroral curtains or fill the sky during intense storms come from oxygen atoms at much higher altitudes, above 200 kilometers, where the atmosphere is so thin that excited oxygen atoms can remain in elevated energy states for up to 2 minutes before emitting their characteristic photons. This long lifetime means the red emissions respond slowly to changing particle precipitation, creating a diffuse glow that can persist even as the green aurora below writhes and shifts. Blue and purple hues in the aurora come from nitrogen molecules, which dominate at lower altitudes where the atmosphere is dense enough that nitrogen, despite being less abundant than oxygen, contributes significantly to auroral emissions. The specific shade of blue or purple depends on which molecular nitrogen transitions are being excited, with some emissions coming from neutral nitrogen molecules and others from ionized nitrogen that has lost an electron in the collision with auroral particles. Very intense auroras can display pink or magenta at their lower edges, where energetic particles penetrate to altitudes below 100 kilometers and excite nitrogen emissions in the denser atmosphere, though such displays are rare and typically occur only during major geomagnetic storms when particle energies are exceptionally high. The relationship between auroral colour and the energy of precipitating particles means that the spectrum of an auroral display serves as a diagnostic of magnetospheric processes occurring thousands of kilometres above. High-energy particles penetrate deeper into the atmosphere before colliding with gas molecules, creating emissions at lower altitudes and shifting the colour balance toward reds and blues, while lower-energy particles are stopped higher up, producing predominantly green emissions. Spectroscopic analysis of auroral light can thus reveal the energy distribution of particles in the magnetosphere, providing information about the acceleration processes that energized them and the regions from which they originated. During the solar storm of March 1989, a coronal mass ejection struck Earth with such force that it triggered auroral displays visible from the Caribbean and caused the collapse of the Hydro-Quebec electrical grid, leaving 6 million people without power for 9 hours. The geomagnetic variations during this storm were so intense that they induced electrical currents in the long, high-voltage transmission lines that formed the backbone of the power grid, currents strong enough to saturate transformers and trigger protective systems that shut down entire sectors of the network in cascading failure. The Quebec blackout demonstrated that space weather was not merely a scientific curiosity, but a genuine threat to modern technological infrastructure, capable of causing billions of dollars in damage and disrupting essential services for millions of people. This event catalyzed the development of space weather forecasting as an operational concern, not just for power grids, but for satellite operations, aviation, radio communications, and GPS navigation, all systems vulnerable to the effects of geomagnetic storms and auroral activity. The challenge of forecasting space weather parallels terrestrial weather prediction in many ways, requiring continuous monitoring of solar conditions, sophisticated models of how solar disturbances propagate through interplanetary space and interact with Earth's magnetosphere, and probabilistic assessments of when and where impacts might occur. Unlike terrestrial weather, however, space weather originates 93 million miles away on the Sun, and current models struggle to predict the detailed structure and timing of solar eruptions more than a few days in advance. The Solar and Heliospheric Observatory, launched in 1995 and stationed at the L1 Lagrange point between Earth and the Sun, provides continuous monitoring of solar activity, detecting coronal mass ejections as they leave the Sun, and measuring the properties of the solar wind before it reaches Earth. This early warning system typically provides 30 to 60 minutes of advance notice before a disturbance strikes Earth's magnetosphere. Enough time to implement protective measures for some systems, but insufficient for comprehensive preparation. The ACE spacecraft, also stationed at L1, carries magnetometers and particle detectors that measure the solar wind conditions directly, providing real-time data on the magnetic field orientation and particle density in the approaching flow, crucial parameters for predicting the intensity of the resulting geomagnetic storm. The orientation of the magnetic field embedded in the solar wind determines how effectively it can couple to Earth's magnetosphere through a process called magnetic reconnection. When the solar wind field points southward, opposite to Earth's northward pointing field at the dayside magnetopause, reconnection proceeds efficiently, opening a pathway for solar wind energy to enter the magnetosphere and ultimately power auroral displays. When the solar wind field points northward, parallel to Earth's field, reconnection is suppressed and the magnetosphere remains relatively quiet despite the solar wind's presence. This dependence on field orientation means that space weather forecasters must accurately measure not just the intensity of solar eruptions, but the subtle magnetic structure embedded within them, information that can only be obtained through in situ measurements from spacecraft near Earth. The Themis mission, launched in 2007 as a constellation of 5 satellites, was designed to resolve the long-standing question of how auroral substorms are triggered and how they evolve. By positioning satellites at different locations in the magnetotail and correlating their measurements with ground-based observations of auroral activity, Themis tracked the sequence of events that initiate substorms, finding that the process begins with magnetic reconnection in the distant tail, some 20 to 30 Earth radii downtail, that launches a disruption front that propagates earthward, triggering the explosive release of energy that manifests as auroral breakup seen from the ground. These findings resolved decades of debate about whether substorms originated in the near-Earth region or in the distant tail, demonstrating that both regions participate, but that the tail reconnection triggers the sequence. The aurora visible from Earth represents only one component of a much larger electromagnetic phenomenon that extends throughout the magnetosphere and into interplanetary space. Satellites have detected auroral emissions from regions well beyond the visible aurora, including emissions in ultraviolet and X-ray wavelengths produced by higher energy processes, and have mapped diffuse auroral precipitation covering vast areas of the polar regions with emissions too faint to see with the unaided eye but contributing significantly to the total energy deposition into the atmosphere. The total power dissipated in the auroral system during a major substorm can exceed 1 trillion watts, comparable to the entire electrical generating capacity of human civilization, energy ultimately derived from the solar wind and temporarily stored in Earth's magnetic field before explosive release. In 2017, citizen scientists observing the aurora reported a new type of display, a narrow ribbon of purple-white light arcing across the sky, distinct from typical auroral forms, which they named Steve, originally a reference to a children's movie but later backronymed to strong thermal emission velocity enhancement. Professional scientists initially dismissed these reports as variant forms of known auroral phenomena, but data from ESA's swarm satellites revealed that Steve was associated with a narrow channel of extremely hot plasma flowing westward at velocities exceeding 6 km per second, far faster than typical ionospheric flows. This discovery demonstrated that even in the 21st century, With comprehensive satellite monitoring and sophisticated ground-based instruments, the Aurora still held surprises, and that amateur observers could contribute meaningfully to advancing scientific understanding. Steve appears to be caused by a different physical process than typical Aurora, involving ion drift rather than electron precipitation, creating optical emissions through mechanisms that are still being investigated. The discovery highlighted the importance of optical observations covering wide areas simultaneously, something that satellite instruments, with their narrow fields of view and traditional ground-based networks, with gaps between stations, could miss, but that a distributed network of citizen observers with cameras could capture. This collaboration between professional scientists and amateur Aurora enthusiasts represents a return, in some sense, to the model that prevailed in Halley's time, when systematic observation by dedicated amateurs contributed essential data to scientific understanding, now enhanced by digital cameras, internet communication, and social media platforms that enable coordination on scales impossible in earlier eras. The Aurora on other planets provides comparative context for understanding Earth's auroral processes and reveals how planetary magnetic fields, atmospheric composition, and solar-wind interaction combine to produce diverse forms of auroral activity. Jupiter's Aurora, the most powerful in the solar system, is driven partly by the solar wind but primarily by the rapid rotation of Jupiter's enormous magnetosphere, which contains plasma from volcanic eruptions on the moon Io, creating a system far more complex than Earth's. Images from the Hubble Space Telescope show Jupiter's polar regions crowned with intense auroral ovals, while the Juno spacecraft in orbit around Jupiter has measured the details of Jovian auroral particle acceleration, finding electric potentials of 400,000 volts, accelerating electrons to energies 10 times higher than in terrestrial aurora. Saturn's Aurora, observed by the Cassini spacecraft during its 13-year mission in the Saturnian system, displays features controlled by the solar wind but also by Saturn's rotation and by the interaction with its moon Enceladus, which injects water vapor into the magnetosphere through its south polar geysers. The Cassini observations reveal that Saturn's Aurora could be triggered by solar wind pressure pulses or could rotate with the planet, and that the magnetosphere contained discrete plasma populations from different source regions, each contributing to auroral activity in distinct ways. These observations demonstrated that auroral phenomena are universal features of magnetized planets in stellar winds, each variation revealing something about the underlying plasma physics, while raising new questions about the diversity of possible magnetospheric configurations. Mars, which lacks a global magnetic field, does not have typical auroral displays, but Mars Express spacecraft has detected localized aurora in regions where ancient crustal magnetization creates magnetic umbrellas that channel solar wind particles into the atmosphere. These Martian auroras are fundamentally different from Earth's, occurring in discrete patches associated with magnetic anomalies rather than in organized ovals around poles, and they provide insight into what auroral processes might have been like on early Earth, before the magnetic dynamo fully established the current field configuration. The MAVEN spacecraft has also detected diffuse aurora, covering Mars's entire night side during intense solar storms, created when solar particles penetrate directly into the atmosphere in the absence of strong magnetic shielding, a process with no terrestrial analogue but potentially relevant to understanding atmospheric loss on planets without protective magnetospheres. Venus, also lacking a significant magnetic field, nonetheless produces auroral emissions detected by the Venus Express spacecraft in infrared wavelengths, created when solar wind particles interact directly with the planet's ionosphere. These Venusian aurora are transient and diffuse, lacking the structured forms seen at Earth and the other magnetized planets, but their study reveals how auroral processes can occur even without the organizing influence of a planetary magnetic field. Uranus and Neptune, visited only briefly by Voyager 2 in the 1980s, both possess magnetic fields and auroras, though the extreme tilt and offset of their magnetic fields from their rotation axes creates auroral zones in unexpected locations, demonstrating that the coupling between rotation, magnetic field geometry, and plasma dynamics can produce configurations never observed at Earth. The understanding that emerged through centuries of observation and recent decades of space exploration reveals the aurora as a manifestation of a vast electromagnetic system, coupling the sun, the solar wind, the magnetosphere, and the upper atmosphere in an intricate web of energy, transfer and conversion. The simple beauty of coloured lights dancing in the night sky conceals extraordinary complexity, involving processes spanning scales from the atomic level, where individual molecules emit photons, to the global scale, where magnetospheric currents flow around the planet, and from millisecond timescales of wave-particle interactions to the 11-year solar cycle and beyond. Each new observation adds detail to this picture, but also raises new questions about mechanisms not fully understood and phenomena not yet explained. The physics underlying the aurora involves some of the most challenging problems in plasma science, including magnetic reconnection, turbulent transport, wave-particle interactions, and particle acceleration in collisionless plasmas, processes that occur throughout the universe in contexts ranging from stellar flares to accretion onto compact objects to the dynamics of the interstellar medium. Understanding these processes at Earth, where they can be studied in detail with extensive observational resources, provides fundamental knowledge applicable to astrophysical contexts light years away, where direct measurement will never be possible, making the aurora not just a local terrestrial phenomenon, but a laboratory for understanding universal plasma physics. The interaction between theoretical predictions, laboratory experiments using sophisticated plasma chambers, computer simulations running on supercomputers that solve the fundamental equations governing charged particle behavior, and observational data from satellites and ground-based instruments creates a feedback loop through which understanding progressively deepens, each element informing and constraining the others. Modern auroral research involves global collaboration on scales that would have astonished the early observers, who stood alone in the cold northern night recording what they saw. Ground-based networks like SuperDARN, comprising dozens of radar facilities spanning both hemispheres, continuously monitor ionospheric plasma motions driven by magnetospheric electric fields, mapping the large-scale convection patterns that transport plasma and energy through the system. All-sky camera networks across the Arctic and Antarctic capture images of the entire visible sky every few seconds, creating datasets that allow tracking of auroral forms as they evolve and move, feeding into models that attempt to predict auroral activity based on solar wind conditions. Magnetometer arrays distributed across continents measure the magnetic field variations on the ground that reflect currents flowing in the ionosphere and magnetosphere above, providing ground truth for satellite measurements and revealing the global structure of geomagnetic disturbances. The data flowing from these systems amounts to terabytes daily, requiring sophisticated automated analysis techniques, including machine learning algorithms trained to recognize auroral forms, detect substorm onset, classify geomagnetic activity levels, and identify anomalous events that warrant detailed human investigation. The transition from individual observers recording their visual impressions in notebooks to automated sensor networks generating more data than any human team could manually analyze represents a fundamental transformation in how science is conducted, one that brings new capabilities but also new challenges in ensuring that important but rare or subtle phenomena are not lost in the overwhelming flood of routine measurements. The balance between automated screening and human interpretation, between the statistical characterization of typical behavior and the detailed investigation of exceptional events, remains an active methodological challenge in modern auroral research, as in many other data-intensive sciences. The question of what new auroral phenomena remain undiscovered cannot be answered, but history suggests that surprises continue to await even in systems that seem thoroughly explored. Steve was only recognized in 2017 despite occurring regularly for likely centuries or millennia, simply because no systematic effort had been made to compile and analyze amateur auroral photographs on the necessary geographic scale. Other rare or subtle phenomena may lurk in observational gaps, visible only from particular locations at particular times, or in wavelength ranges not routinely monitored, or in statistical patterns that emerge only from analysis of decades-long datasets. The auroral substorm, though now intensively studied, still reveals new features as observational coverage improves. The details of how substorm onset propagates, whether all substorms follow the same sequence of events, and how the coupled magnetosphere-ionosphere system organizes itself during substorms remain areas of active investigation where competing hypotheses guide observational campaigns and theoretical developments. The future of auroral research involves increasingly sophisticated space missions capable of measuring plasma conditions in 3 dimensions across large volumes of the magnetosphere simultaneously, something that current satellite constellations approximate but do not fully achieve. Proposed missions would deploy dozens of small satellites throughout the magnetosphere, creating a distributed sensor network that could track how disturbances propagate and how energy flows through the system on timescales and spatial scales currently impossible to resolve. Ground-based observations are advancing through deployment of new instrument types, including coherent scatter radars that can measure ionospheric plasma parameters with unprecedented altitude and temporal resolution, and optical instruments sensitive to specific emission lines that reveal particular aspects of the auroral process. The integration of these diverse data streams through sophisticated data assimilation techniques, similar to those used in weather forecasting, promises to create comprehensive nowcasts and forecasts of auroral activity, beneficial both for scientific understanding and for practical space weather applications. The auroral research community faces an interesting challenge in that the phenomena under investigation are becoming increasingly relevant to technological society at the same time that fundamental questions remain unanswered about how the system works. The practical need for space weather forecasts to protect power grids, satellite assets, and communication systems drives funding and attention toward operational capabilities and relatively near-term improvements in prediction, while the scientific impulse drives toward deeper understanding of fundamental processes, an understanding that may not yield practical benefits for years or decades. Navigating this tension between applied and basic research, ensuring that the pursuit of immediate applications does not starve the fundamental investigations that enable long-term progress, requires judgment and balance from funding agencies and researchers alike, a challenge shared with many fields at the interface between science and technology. The indigenous peoples who first observed the aurora and developed rich cosmologies around it remain in the Arctic regions where auroral displays are most frequent and most intense, their communities now navigating the challenges of climate change, economic development, and cultural preservation while maintaining connections to traditional knowledge systems that embedded auroral observations in broader understandings of environmental relationships. The integration of traditional knowledge with Western scientific approaches represents not just an epistemological exercise, but a practical opportunity to draw on observational traditions, extending across time periods much longer than the historical record of instrument-based science, potentially revealing long-term patterns in auroral activity correlated with climate variations, with changes in Earth's magnetic field, or with other environmental factors. Achieving such integration requires overcoming historical legacies of colonialism and scientific paternalism, developing collaborative frameworks that respect indigenous intellectual property while enabling knowledge exchange, and recognizing that different knowledge systems may organize and communicate information in fundamentally different ways that do not simply translate into each other, but require patient dialogue to bridge. The question of whether auroral activity has changed over historical time scales remains surprisingly difficult to answer, despite extensive historical records of auroral observations extending back millennia. Ancient Chinese astronomers kept detailed records of unusual celestial phenomena, including probable auroral displays. European and Middle Eastern chroniclers recorded dramatic aurora, visible at mid-latitudes during intense geomagnetic storms, and indigenous oral traditions encode information about auroral behavior across generations, yet extracting quantitative information about long-term trends from these diverse sources presents formidable challenges. Historical observers did not use standardized measurement protocols. They selectively recorded unusual events rather than typical conditions. Their geographic coverage was highly non-uniform, and their interpretive frameworks varied widely, all factors that complicate attempts to reconstruct past auroral activity levels for comparison with modern observations. Proxy measures of past geomagnetic and solar activity provide alternative approaches to reconstructing long-term auroral history. Ice cores from Greenland and Antarctica contain chemical signatures of intense solar proton events that penetrated to polar lower atmosphere, creating isotopic anomalies that can be dated and correlated with other records. Tree ring radiocarbon variations reflect changes in cosmic ray flux modulated by solar magnetic activity over the 11-year solar cycle and longer timescales, providing an indirect measure of solar variability extending back thousands of years. These proxy records suggest that solar activity has varied considerably over recent millennia, with periods of enhanced activity like the medieval maximum and suppressed activity like the Maunder minimum of the 17th century, when sunspots nearly vanished for decades, presumably affecting auroral occurrence rates. Though the quantitative relationship between solar activity measures and auroral frequency is not simple enough to allow precise reconstruction. The Carrington Event of 1859 remains the most intense geomagnetic storm in the modern observational record, but analysis of ice core nitrate spikes suggests that comparable or even more intense solar storms may have struck Earth in prehistoric times, including an event around 775 CE that produced radiocarbon anomalies an order of magnitude larger than typical solar events. If such an event occurred today, striking a technological civilization dependent on electrical grids, satellites, and radio communication, the impacts could be catastrophic, potentially causing trillions of dollars in damage and disrupting essential services for months or years in affected regions. The probability of such extreme events remains poorly constrained because the modern observational record spans only decades, an insufficient baseline for characterizing the frequency of rare but high-impact solar storms, leaving risk assessment dependent on extrapolation from limited data and theoretical models of solar magnetic energy storage and release. The aurora continues to inspire wonder in those who witness it, whether indigenous hunters, continuing traditions extending back countless generations, tourists travelling to Arctic destinations specifically to see the lights, or scientists deploying sophisticated instruments to measure its properties. This multi-layered significance, aesthetic, cultural, spiritual, scientific, practical, ensures that the aurora remains an object of intense interest, even as understanding deepens and mystery diminishes. Each generation encounters the aurora within its own context, seeing in it reflections of contemporary concerns and opportunities while adding new layers to the accumulated tradition of auroral observation and interpretation that now extends across all of human history and across the globe. The lights that dance in the polar sky are both the same phenomenon that awed our distant ancestors and something new, revealed in ever greater detail by each advance in observational capability and theoretical understanding, a bridge between past and future, between Earth and space, between the empirical and the numinous.